So last time we saw that the due group is basically the maximal ideal space of the L1 of G. So it inherits a weak star topology as the due space of the L1. So it has it's a locally compact Hausdorff. Okay. So oftentimes the topology as a weak star topology is very difficult to work with. So I would like to talk a little bit more on the topology on the due group. Okay, there's actually a better way of describing it. Some authors call it the compact open topology. Okay, so we're going to see why that's the case. All right, so this is going to be fairly technical on the topology stuff. All right, so let's get started. So let's just recall the following. The G hat, we identified it as the maximal ideal space of the L1 of G that's contained in the L1, the due group, which is basically the L infinity with the weak star topology. So as we know about the weak star topology, so let's describe its neighborhood basis. So let's say for every phi 0 contained in the G hat, what's the basis is basically you test against a bunch of functions. So you take, say, f1 up to fn inside the L1 of G, and you say, well, let's take some epsilon greater than 0. Let's just use the notation. So let's define this u of I test against f1 up to fn, centered around phi 0, and then let's allow epsilon. Okay, these are essentially everything, all the phi inside G hat, where phi and phi 0 are close enough against these fi. Okay, so in other words, if you integrate each of these fi against the difference between phi and phi 0, okay, so this the d mu is the Haar measure. Okay, you fix some Haar measure again. This is going to be less than epsilon for all I going from 1 to n. Okay. So this is going to be a neighborhood basis for your topology at phi 0. Okay, so these are they are all open, and it's a basis of the topology, the weak star topology. And you can see this is kind of difficult to describe. Okay, if you want to make it any useful, this topology is super difficult to work with. Okay, so we need to start describing what's an alternative way of describing a topology on the space. So first of all, I need a proposition. So let's do the following. So if I consider this map, okay, so if I consider the x, I take an x from the G and I take a character from G hat, okay, so I consider it as G times G hat, and then just map it to phi of x, okay. Of course, this is inside the complex number, where you can even say that's the unit circle. All right, so you put on the left-hand side, you have the product topology. On the right, you do the usual topology on the unit circle. I claim that this is going to be continuous. Okay, so first of all, this evaluation map is joint continuous. All right, so here is the proof. Okay, so to prove this fact, well, I basically need to find some open neighborhood of x and phi so that inside this neighborhood, the evaluation is kind of close enough to the phi x. All right, so let's observe the following first. Okay, let's observe. Suppose I have a f inside the L1 of G, and I give you any phi inside the due group. Okay. So if I just do the following, if I do the integral of f phi d mu against the Haar measure, and then I multiply some fixed phi of x, okay? So this is just equals to let's do the integral, say, ft phi t dt, and then everything I multiply by phi x. Of course, you can move the phi x inside, and phi is multiplicative. So phi t phi x is phi of xt. Okay, so this is the integral of f of t and phi of xt dt. And you can do the left translation. You can basically replace t by x inverse of t. Okay, so because your dt is translation invariant, this becomes x inverse t phi t dt. And this, you can again think about this left translation of f as Lx of f, evaluate at this point t, and then phi t dt. Okay, so they're essentially the same. Okay, so now you observe that what's nice thing about this is that now you see this little phi of x is now a ratio of two things. So one is here and the other is that. Okay, so the left-hand side is integral. You can take some f, let's make it non-zero. So as long as the right-hand side is a continuous function, joint continuous function for x and phi, then your little phi of x is going to be continuous. Okay, so we have that this map x phi to phi x is continuous. That's if and only if, let's define the right hand side, let's call it big phi. Let's fix an f. Okay, I define big phi f at x and phi. That's equals to this integral of last translation of f, integrate and multiply against this phi respect to the Hart measure. Okay, if and only if this map is continuous. Okay, so that's pretty clear. So the good thing about this is that this big phi of f is essentially integrating some left translation of f. Okay, so I just need to show that for every f, this is continuous. Okay, for every f inside L1 of G. Okay, so that suffices. All right, so now let's fix f inside L1 of G. Okay, and let's fix some point x0 and a little phi 0 inside G cross G hat. Okay, so I want to find some neighborhood where this big phi f evaluates phi of big phi f evaluate x and little phi is close enough to x0 and phi 0. Okay, so that's what we want to show. All right, so let's do the following. So let's say for every epsilon greater than 0, let's fix an epsilon. And for your x0, well, there exists a, because the left translation we showed is continuous in terms of this x, okay? Not only in infinity norm, but also in one norm, in fact, in p norm as well. But in any case, because of that is continuous, so this there exists an x0 inside some u open neighborhood of this x0, so that for all x inside this u, I have the Lx of f minus the Lx0 of f. Their one norm is less than epsilon over 2, okay? That's simply because the left translation is continuous on the L1 space. And there is also exists some neighborhood, let's call it W, okay? That's some open neighborhood of the phi 0, so that because of the weak star topology, so for every phi inside your W, you have that the integral of, if you just fix this Lx0, okay, you test it against that, the phi and phi 0 should give you very similar integral, okay, so that's less than epsilon over 2, okay, so that's coming from the weak star topology. All right, so now we have these two estimates, so now let's consider for every x inside this u and this phi is inside w, then what do I have, okay? So I want to estimate the integral of the Lxf against this little phi d mu minus the integral of the x0f phi 0 d mu. Okay, so that's what I'm going to integrate. All right, so I can divide it into two parts. Okay, so it's going to be less than or equals to the first part as use the integral of the Lxf minus the Lx0 of f. Okay, I tested against phi d mu. Okay, and then the second part is going to be, now I have the Lx0 fixed, so the integral of Lx0f, and then I have a phi minus phi 0 d mu. Okay, so this is just triangle inequality. But the first thing, if you look at the first integral, is going to be less than or equals to the integral of the absolute value. And again, because your phi is a character, so the norm of phi is always 1 in the unit circle. So you just end up with the norm of the Lxf minus Lx0f d mu. And that's going to be less than, this is essentially just less than or equals to this one norm, and we know this one norm less than epsilon over 2, so this is epsilon over 2, okay? And the second one, by our choice of this W, this neighborhood of phi 0, we know the second one is also less than epsilon over 2, so everything is less than epsilon. Okay, so we finish the proof.